Okay, so let's go ahead and take a look at our Unit 7 review, which is our last unit of the year. Not the end of the year, because we'll be doing a lot of released AP tests and just review of various concepts, but it's the last standard exam of the year. And for some reason, this thing has never been put out before. So let's go ahead and remedy that situation. So we've got this toy car here that's sliding down a ramp and coasts to a stop after 5 seconds. And its velocity is modeled this way. Now, one thing that I thought was kind of interesting is that like I wanted to do something more with this problem, but based on its story here, the car is sliding backwards, so clearly its velocity will always be negative the entire time. But when you talk about how far its distance is traveled, then that would be then modeled as a positive quantity because distance between values is always done as a positive entity. So let's go ahead and find the integral of that, because remember, the integral of your velocity would be your position function. So we're going to find out what happens if I integrate v of t dt. So my nice easy integral would be 1/3 t cubed minus 0.02 over 4t to the fourth, evaluated from 0 to 5. Now, one thing that's interesting about this particular piece right here is that 0.02 is actually 2/100ths. So if I took 2/100ths and I divided it by 4, that would be like 2/400ths, or in other words, 1/200th. Hopefully I did all that correctly. I think I did. And we're going to go from 0 to 5. And by doing just a little bit of mathematics, we got 125 over 3 right here. And we're going to have minus 625 over 200 because 5 to the fourth power is 625. We do need to do a little bit of common denominator game, also a little bit of simplification. And I got 125/12 feet. Generally speaking, we got a good answer right here, but this would be a better answer. Okay, so moving on to number 2, we're going to be finding the area enclosed between two curves. So you want to remember, every time we're talking about the area enclosed between two curves, we always want to think about the far curve, or the one that is farthest away from the axis that we're considering, and the one that is the closest. So we have y equals x plus 1, which is a pretty simple little line going like this. We have y equals 3 minus x squared. So we've got this little parabola that hits up here at 3, and it's coming down this way, right? Well, when I first looked at that, I'm like, I don't really exactly know where it hits. So I'm not sure exactly, is it going to hit before the x-axis, or is it going to hit after the x-axis? So I'm just giving you a general idea. But what I see right now is that the curve is further away from the x-axis in general, and the line is the closer of the two. So what I need to do is I need to take the far one, which is 3 minus x squared, and I need to subtract the close one, which is x plus 1. Now, of course, before we can do anything else, we really do need to find what these places are in these two locales that actually, where do they intersect to know what my bounds are. So let's see. Let's go ahead and take x plus 1, and let's set it equal to 3 minus x squared. This is really, and honestly, one of the reasons we kind of sometimes, I refer to calculus as like algebra 3 or algebra 4, because we frequently find ourselves needing to draw on some old experience from previous classes to come up with this. So I noticed that this was a pretty nice factorable quadratic. And so I noticed that those points of intersection, one of which was at -2, and the other one of which happened at +1, are the two values that would solve this. So I need to integrate from -2 to +1. Now, you could integrate this as is, or sometimes people will choose to simplify it a little bit first. And I think that's what I would like to do. is rewrite this as negative x squared minus x, and I got a 3, but I subtracted 1, so I have 2. So that means my antiderivative is going to be 1/3 x cubed with a negative, a 1/2 x squared, again also having that negative, plus a 2x, evaluating from -2 to +1. And, okay, plugging it in is not that big of a deal, but my notes reflect that value, in other words, capital F of 1 minus capital F of -2. In other words, the evaluation of the antiderivative of 1 minus the evaluation at -2 gave me 9/2. I'm pretty sure that is the right answer. We could validate that under a calculator, but for the sake of time, I'm pretty sure those answers are correct. Okay, moving on to number 3. I wanted to try to get the first 4 of these done. So we, on number 3, are going to find the area of the region enclosed by these 2 simple sine waves. Now keep in mind, this one has an amplitude of 2, whereas this one has an amplitude of 1. The period of this guy is 2 pi, but the period of this thing is 1 pi, which actually works okay because we are only going to see a half of this period, but we're going to see the whole period of this particular sine wave right here. So I think I'm going to start with this guy right here. The sine of that one, by the time it reaches pi, will have gone all the way up to +1 and back down, as it turns out, to -1. And of course, we should have a sine wave that has this generalized feel. Okay, so there is my original sine wave. For this guy, I'm going to go ahead and change to purple. I don't know if this is going to come across in the video well as a distinctly different color, but that means it has an amplitude of 2, but it only has a period of 2 pi, which means it's only going to complete half of its cycle by the time it reaches that. So it's going to have a peak right here in the middle. So it's going to look something like this. And we are looking for the area enclosed between those 2 curves, which is this region right in here. So not a particularly complicated problem, but we are going to then take the far one. So in general, the far one would be the one with the shorter period minus the closer one right here, which is the one that has the quicker period. And we're going to, of course, evaluate that from 0 to pi. This is actually saying in 0 to pi, but it really should be like on that interval from 0 to pi, okay? So the antiderivative of a sine, we have to be really careful because we're not taking a derivative. The derivative of sine is cosine, but the antiderivative of a sine is a negative cosine. And the antiderivative of this sine would be a positive cosine, but when you take the derivative, you get an extra 2 by the old chain rule, but that means an antiderivative is going to need a 1/2. Now, what I would like to do, and I call this a habit of mine, it's just good mathematical practice. Think about it. When back in elementary school, when you were asked to divide, you would then multiply to check your answer. Well, we're much better at derivatives than antiderivatives. So what is the derivative of a cosine? Would be a negative sine, but then we get a double negative, and that works. Same thing here. The derivative of cosine is negative sine of 2x times 2, and that would cancel that 1/2 out, and that works. So we are then going to evaluate that from 0 to pi. And so when we plug this in, interestingly enough, this is going to be f of pi. In other words, let's plug in pi into the whole thing. When I plug in pi, the cosine of pi is -1. So that gives me a +2. But the cosine of 2 pi is actually exactly the same as taking the cosine of 0, and that is actually 1. So this one was a negative times a negative, and this one was already positive. So it looks like so far I've got 2.5 coming across. But to that, I need to add what I get, excuse me, let me fix that. I need to subtract what I get when I take f of 0 itself. So when I plug in 0, the cosine of 0 is 1, so I have negative 2. And when I do this, I get the cosine of 0 again is also 1. So putting that all together, be very careful here. I've got a 2 minus a negative 2, which is 4. Then I've got a half, and I'm subtracting a half. So I guess just nicely enough, it perfectly came out to be the number 4. Okay. Now here's the last one. Now again, we probably should specify that this is 100% intended to be a calculator forward question. I don't have the ability to solve this problem reasonably well, taking a really strange exponential story, setting it equal to a quadratic. That's just not going to happen. So what we're going to do in here is let's go ahead, and hopefully this is going to come across well. Let's go ahead and take a look at the two curves. The first one being 3 raised to the 1 minus x squared. The second curve being x squared minus 3 over 10. Now, I'm doing this without really spelling it all out, but keep in mind, you'll notice that I put the exponent as well as the numerator in parentheses just to ensure that that whole block was where I wanted it to be. Now, right here, there's a hint in the paper. You can't see what I'm pointing to, but there's a hint about the range that I want to do, or the window I want to do for my calculator. So it's saying, let's go ahead and make my x values go -4 to +4, and let's let my y values go from -2 to 3.5. Now, this thing right here was not really necessary. We didn't have to give you that picture. We could have figured it out, but this is kind of my picture that we have. And I'd like to find the area under that. But the first thing that I would like to notice is when I do the far one, which is the far one, I guess, let's see, it was the blue one. It was the exponential was on top. So the exponential curve was the far one, and the parabola was the close one. So I'm going to do the exponential curve. We're going to subtract the parabolic curve. But I need to figure out the bounds. Well, the first thing, though, that I notice is this is a symmetric interval. It's a perfectly, in fact, if you look at them, they're both even functions. Keep in mind, if you looked at f of -x, it is f of x for both. Replacing that x with a -x, or that one, doesn't do anything. So we know both sides of the curve are identical. So I just need to figure out what is happening from 0 up until this point of intersection. So let's do that. So let's go over here to, let's calculate the intersection of those two curves. Now it's 1.893. I'm going to write that down. But even though I wrote it down, I'm not going to use that value, because what I'm going to do is I'm going to store that information that it already did as alpha A. So there we go. So now I can do my math 9. Remember, that was my numerical integral. I'm going to go from 0 up until A. We are going to then take the far curve, which was my exponential. Got to make sure that I have that right. My far curve was y1. So we're going to do alpha trace y1 minus alpha trace y2 dx. And now I don't really have to work very hard, because my calculator knows what y1 is, y2 is, it knows what a is. And of course, the only thing I haven't done is I haven't multiplied that answer by 2, which I could have put in earlier. So I got a cumulative answer of 5.731 square units. And again, this should be units squared as well, right? All of these that are area between curves should be units squared. I was talking to my son recently, and his professor ended up dinging him on some of his answers because he didn't specify square units on some of these problems, even though his numbers were correct. So that will do for page 1. We'll be back for page 2.